So just wanted to make sure you can see my screen.
Yes, and now you can go into full screen mode. Okay, 5 minutes starting.
Okay. So hi, so I'm Farhad Mohsin from RPI. And I know there's a lot to unpack in that title. We're going to be talking about group fairness and privacy in voting rules, and also some sort of machine learning things in there. But yeah, I'll try to go, we can stay at the high abstract level. So think about this preference profile where we have 6 agents, but the agents are clearly divided into subgroups by some sort of features. In this case, we have the blue men who all have the same preference. We have the red women who all, again, have the same preference. Now, traditional voting rule in this case would maximize some measure of efficiency. For example, A here is a as a winner. Plurality would also choose A as the winner, but we can consider that, considering the group identities, A would be a really unfair winner because the minority group, the red women, absolutely does not like A and least prefers them. So, but if we look at the preference profile really quickly, we can see that B can be considered somewhat more of a fair winner because B is somewhat well preferred by both groups of identities. Now, traditional voting rules usually don't care about this member identities, but our question is, when we think about this group memberships and then think about the preferences, how can we design a voting rule that maximizes efficiency like traditional rules, but at the same time thinks about fairness and also maybe some privacy constraints. So we want to care about the group identities here and then think about what we can go from there. So we start by basically looking at it from the opposite direction. We want to care about fairness, but we present a notion of unfairness, and from there we work on top of it. So our unfairness of a voting rule is basically the worst case imbalance that it can get from the winners of that voting rule. What is imbalance? Imbalance is the ratio between difference of the average utilities that the two groups get. So here P1 and P2 would be the preference profiles of the two groups, and the ratio of that, the average utility for the whole population. So a quick numerical example based on the example we had before, the utilities presented here are basically border scores. We see that, like we said, the alternative B is giving low imbalance and can be considered more fair. And so ideally, we would want this case where we all have low imbalance, but also very high utility. So that's what an ideal thing should get. But we are thinking, okay, does that really happen? Can we really get high efficiency while low voting rules? So first, analyzing traditional voting rules, we get some theoretical results that are not really that good. In worst case, over all possible preference profiles, and for some utility function assumptions, or the only assumption we really make is that the utility function is homogeneous and rank-based. Everyone has the same utility function, rank-based utility function. So yeah, the negative result is that traditional voting rules, while maximizes some sort of notion of efficiency, can have max unfairness values. So it can be completely unfair. So we thought about, okay, well, let's go to the other spectrum where we can have fair voting rules. Completely fair always chooses the one with the least imbalance. That gives us something that can give very low worst case efficiency. So we basically get two spectrums of voting rules according to our new notion of fairness. So that gives us an idea about designing new fair and efficient voting rules. And we have 2 techniques. I'll not go to the constrained one first, because that's rather simple. I'll go to the other direction that we went into, and we are using machine learning, specifically classification type algorithms to design new voting rules. So what we do is we denote voting as sort of a multi-class classification problem. The candidates would be the different labels, and we would want to class voting as multi-class classification problem. We can create synthetic training data, like synthetically creating preference profiles, choosing winners based on different properties that we want, and then using the synthetic data, learn a voting rule or a classifier using whatever suitable classification algorithm that we can get. The good thing about this is it does not really depend on what our efficiency measure is. It can be conducive efficiency, it can be some sort of social welfare under any of the positional scores, or even other efficiency measures that we can think about. It does not really need to depend on our notion of fairness. It can depend on other notions of fairness, etc. But this framework can work with everything and can come up with new voting rules. I'll not really talk about privacy, but let me just say that in our work, we consider local DP and the effect of local DP along with fairness and efficiency. But yeah, going experimentally, we see that, okay, traditional voting rules and fair voting rules, like we said, are at the opposite spectrum. Traditional voting rules has high efficiency, low fairness. fair voting rules has high fairness and low efficiency. Using our techniques, both of our techniques are shown here, the orange are the machine learning ones that I talked about. We can get voting rules at different levels of efficiency and fairness. So empirically, we showed.
And that's a good place to stop. 5 minutes.
And I'll just stop there. Thank you.
Right. Okay, sorry it was abrupt, but I think we got to the last slide.
Yes.
Okay, questions for the speaker. So feel free to just ask. Okay, so there's a question in the chat. Farhad, would you like to read it?
Okay, so the question is, there are two actors of an election, namely candidates and voters. The model discussed seems guarantee fairness with respect to candidates. What about fairness with respect to a predefined population of voters? I would actually say that our model specifically looks into fairness with respect to voters. We are assuming some sort of utility functions, and based on those utility functions from the voters, we are trying to get to candidates who are who give similar utilities, so are kind of equitable to both groups of voters. So in a way, we are trying to be fair towards groups of voters altogether. Does that answer your question?
Yes, thank you so much. So just a follow up then, what about fairness with respect to the candidates? Like we would want male candidates and female candidates to win.
So I would say that fairness with respect to candidates in proportionality, etc., is already kind of discussed in other voting rules or other literature already. So this is, we felt that proper representation among candidates is something that's already been discussed quite a lot. We can probably add that in a compositional manner on top of what we have, but we thought that, okay, looking at it from group perspective of the voters is probably something new, and let's focus on that for now.
Okay, thank you, that makes sense. Thank you so much.
Okay, Sonja, you can start sharing. So meanwhile, a quick clarification question. So do your voters come with labels? So are you trying to be fair to predefined groups of voters or to all voters simultaneously?
So predefined groups of voters, basically.
Okay, very good. So Sonja, you can start. We can't hear you.
Am I unmuted now?
Yes, you're unmuted now.
Sorry. I'll just talk about one, maybe two results that are part of my master's thesis. The topic is identifying the lines from, single peak preferences with high probability, and I'm supervised by Edith. So just a very brief reminder of what single peak on a line was, just so that you can follow. This is a line, this is some candidates, and basically choose your favorite party, and then out of two parties that are more left than your favorite party, you prefer the one that's less left. Out of two parties that are more right than your favorite party, you prefer the one that's less right, and that's kind of the general idea of how the preferences are supposed to be structured. So now I'll just mention a few sort of popular distributions over the preferences single peak on a line. So say the line is P, you've got M candidates, and V is the set of all votes that are single peaked on the path P. And in the uniform distribution over V, just as the name says, just all of the 2 to the m-1 votes single peaked on P are equally likely. Sort of another popular distribution in the literature is the random peak model, in which, you pick the peak of your favorite candidate with probability 1 over m equally likely, and then afterwards, the candidate to the right next to you and to the left next to you is equally likely. And kind of after you've picked a segment of consecutive candidates you've ranked, again, the next right and the next left is equally likely until you reach a leaf, and then you just have to rank the rest at the bottom. And so a question from a paper in Chennai 2019 was that, given votes sampled from the uniform distribution over V, can we efficiently, in terms of sample and computational complexity, identify P with high probability? Now, identify means that if you have a set of votes that are a subset of V, the compatible votes with P, so a subset of votes that are single peaked on P, that they identify P uniquely, meaning no other path the vote is not single peaked on any other path. And so One result is basically that for any error parameter, we can identify P, so identify it uniquely with a sample size of or a log of M over delta with probability at least 1 minus delta. But so, yeah, this is one distribution. What about, the random peak model or even other asymmetric distributions? Well, our analysis sort of generalizes to more general class of distributions. And in particular for the random peak model, it does imply the same order of sample complexity. However, the random peak model actually is not such a hard distribution. You can actually further reduce the sample upper bound to log of 1 over delta, and this is also tight, so there's also an easy explanation why it's a lower bound. And the kind of general class of distributions and the characterization we get from our analysis, I'll omit here because it's a bit difficult to state, but essentially you don't need the distributions to be asymmetric, and the sample complexity upper bound we get then just kind of depends on some parameters of the distribution. That's all I'll say about that. And then another one thing that I'll mention is, as long as I still have time, is mixture models. So say, for example, you'll get with probably P samples from some distribution single peaked on a line that you know, and then with probably 1 minus P samples peaked on a line that you don't know. And now you don't want to identify or learn the line that you don't know. For example, the known line is the party social response, the unknown line is the COVID response, and you don't know how that would be ranked yet. I'm not sure how to, oh yeah. So however, in the worst case, actually there can be up to 2 mixtures compatible with a sample, so uniqueness doesn't really work. But now what we want is to instead kind of do as good as we can. So identify with best certainty. If there's 2 possibilities in the worst case, we want to identify those. And we also did that. I'm not sure how much time I have left, but sorry?
20 seconds.
I mean, basically that was all. I didn't write any more because I thought I wouldn't have time.
Okay, perfect timing. Questions for Sonja?
I can't see.
So discussion in the chat, yeah, seems related to the previous talk. Okay, questions, anyone? I don't think I have any. Okay, not as yet. So I think kind of having to ask questions in a 2-minute interval is a bit stressful. Okay, so shall we continue with the next speaker then? So who is next? Is it Michał?
Yeah, that's me, I think.
Then feel free to share.
Just please tell me whether you see my screen.
So I'm seeing something black.
Is it not black anymore?
Okay, no, it's fine now. Feel free to start.
Okay, so thank you so much. It is the title is Control Problems for Two-Dimensional Euclidean Elections, and it's a kind of a continuation of a project that we started with other people, and it is very much in progress with Péter Leizerovich. So yeah, we have N candidates and N voters as usual, and for this talk, assume that we have linear preference orders for each voter over the set of the candidates, or the position of a candidate in the preference order denotes its place on this preference order, and the top position is position number 1. And what I want to present is the result concerning the plurality rule, where you give a score equal to 1 to each candidate if he's in the top position of a given voter, and you sum over all voters, and the winner of the election is the candidate that gets the higher score with respect to this summation. And what we consider are Euclidean elections, and we say that voters have t-dimensional Euclidean preferences, where t is a natural number. If for every voter and every 2 candidates, if it holds that the Euclidean distance between the ith candidate and the voter v is less or equal than the Euclidean distance between the jth candidate and the voter v, then the position of the ith candidate in the preference order of the voter v is better than the position of the jth candidate. So the closer the ideal point of the candidate ci is to the imagined ideal point of the voter V, then the higher it is in its preference order. And the intuition here is that for any agent, voter or the candidate, the point describes this agent's ideal position in some space of issues that is T-dimensional. And the problem that we consider is the constructive control by adding candidate for plurality rule here. And given an election with registered candidates and unregistered candidates that might be added like Nader in 2000, an obvious example, and the given candidate, we ask if it is possible to find a set of unregistered candidates that could be added so that their size is to be limited, such that in an election over C candidates plus this subset of additional unregistered previously unregistered candidates, the candidate P will be the winner under the plurality rules. And the other variants of those control problems for various election rules are destructive instead of constructive when we want to make the candidate P to become a non-winner. For sure, we can delete candidates instead of adding them, and we can also add or delete voters instead of candidates. And the classical results are that deciding constructive or destructive control by adding or deleting candidates is NP-hard. So these problems are resistant, so to say, and deciding the control problems by manipulating the voters is a polynomial. However, there are results that say that, for example, for single peak preferences that were mentioned, deciding the constructive or destructive control, for instance, for plurality rule, has a polynomial time solution. So kind of a natural question is if it's in general NP-hard to compute, but it becomes tractable for single peak preferences, so also for Euclidean preferences on a line, then the question is it rather the one-dimensionality that is responsible for that, or perhaps the domain restriction to Euclidean preferences that makes these problems tractable, sorry. And the main result is that, for example, for plurality rule, whenever we go even in the restriction to Euclidean domain to 2-dimension, then constructive control by adding candidates becomes intractable. So deciding it is NP-hard even if the voters have 2D Euclidean preferences. And I won't get into the details, obviously, but to get to the result, we do the reduction from vertex cover problem for almost integral penny graphs. And since I have only half a minute, I will just say what a penny graph is. And it is basically defined by a set of unit disks. So the centers of the unit disks are vertices, and they have an edge between them if their disks touch but not overlap. And an important lemma to do the construction is that we can put a penny graph in the Manhattan metric, so to say, so that all the vertices are at integer coordinates and edges are drawn with vertical and horizontal line segments. And now I'll end with that. So thanks.
Okay, thanks, Michał. Perfect timing. Any questions? Okay, so what's happening in the chat is now relating to Sonja's talk. Kind of, there's always this delay. So I have a question. So you have a recent paper that was presented in COMSOC that also proved hardness is out for 2D. So do you think you might be able to define the general features of problems that remain hard in 2 dimensions? Do you have an intuition of what that might be?
So the thing here is now that the reductions that we have to get the hardness results are almost always related to those penny graphs. So it is the case that there is a subclass of vertex cover or independent set or related problems for very planar graphs that is still intractable, and 2-dimensional Euclidean preferences seem to closely correspond to that. So despite the fact that they have nice structure in the sense of being derived from a location in 2 dimensions, they correspond to graphs that have problems that are intractable, even though they are very planar. So but that's only the intuition at this stage.
But basically, whatever is proven by hardness reduction from vertex cover should remain hard in 2D. Is that what you're saying, or not quite?
I mean, is the question is everything, any hardness result concerning vertex cover that should transfer to D? No,
yes, so if you prove a hardness result of a social choice problem by a reduction from vertex cover, should it survive in 2D or not necessarily?
It depends on what subclass of graphs we are discussing. I mean, that those almost integral penny graphs seem to be very, very convenient to work with, to put on agents like voters and candidates during the combinatorial part of getting your hands dirty and doing the reduction. So I don't yet have I'm not in a position to respond to such a general claim positively.
Okay, so planar vertex cover, but okay, so let's drop that. So Eyal, would you like to share your slides? And remember to unmute yourself when you start talking.
Yes. Do you hear me?
Yes.
Okay, so my
But
talk
we don't
is
see your slides. We don't see your slides yet.
Okay.
Yes.
So my talk, yeah, sorry. My talk is about deliberation, and the motivation here is if you just do like if you just forgot the name, if you just choose a winner of an election over the agents without deliberation, you can get some kind of winner, and not necessarily fair or suitable for everyone. And that's why there is a need for such a process of everyone deliberating, talking to each other and convincing each other to change their opinions, and getting close to each other in what we define as a metric space, and their opinions getting close to each other. And I'll define this process now. So we define the agents, each having an ideal point in a metric space, and the deliberation process has two steps. The first step, we apply the voting rule, which gives us a compromise point, an ideal point, which is agreeable sort of for everyone. And then everyone approaches this compromise point by epsilon, which is chosen arbitrarily in the beginning of the process. And if it was already close, less than epsilon to that winner, it just moves over to the winner. And the process ends if everyone are in consensus, or just lasts forever. I'll give you an example. Let's say the metric space is Z, or the whole numbers, and the voting rule is the mean rounded down. And the initial points are 3, 5, and 8. So the mean rounded down is 5. So the winner, which is W, is 5, and the V0 is 3, V1 is 5, and V2 is 8. In the next iteration, 3 moves to 4, and 8 moves to 7, and 5 stays in the same place. And after 3 iterations, everyone is 5. The winner stays the same because the mean just stays the same. 3 goes up, and 8 goes down. So I hope this example is clear. We achieved the two general results. If the winner in any metric space and voting rule moves slower than epsilon, strictly slower than epsilon, then consensus will be reached. This is because the agents will catch up with it eventually, and the proof is because the sum of all all distances will go down strictly decrease. The next general result is when in every metric space, when the voting rule is chosen to be one which minimizes the sum of all distances for the agents, again, convergence is always reached. This is because the winner always stays the same point in every iteration. This is our list of results. In the left column, this is the metric space, and then the distance, then the voting rule, and the V symbolizes if convergence is always reached in the worst case, and then the worst case time, number of iterations. The R is Euclidean spaces, and then you can see variable number of winners, multi-winner. Variable number of winners is when you can choose how you can choose from a number of candidates, and you can choose how many candidates you want. And multi-winner, we can choose k candidates out of a list. And the social welfare function is ordinary. You can choose a permutation over the whole list. And I want to focus on specific results on ordinary elections. When we prove the quite general result by a potential function over a class of voting rules, which we call the score rules, which is where the voting rule is made by giving a score to each candidate, and then getting the winner by sorting the scores decreasing in a decreasing order, and then the winner is the one with the best score, and then sorted by this. And we proven that by a potential function that you can read this that
it reached the end of 5 minutes. Sorry,
okay.
Thanks. Sorry, I had to interrupt.
This is the last slide. Okay.
Right, but let's leave a little bit of time for questions. So can you please unshare?
Okay.
So what I see in the chat, I think still relates to Sonja's talk. So any questions for Eyal? Okay,
so
questions in the chat.
People...
So Eyal, can you see the question in the chat?
Yes.
So can you read it?
I wanted to write. Yeah, we didn't focus on the line and changing the result, but we did prove that with certain models, certain metric spaces, the endpoint, the final winner will be a definite one. So when in some cases the winner just doesn't change, like in Chennai, and in every voting rule which is argmin, and in some other cases. So in these cases, the final winner just is known from the start, which is the first winner. And in other cases, we can limit the space which the winner would be. So we didn't focus how you can change it, but we limit where it would be.
Okay, great. Thanks, Eyal. So let's unmute and thank all speakers of the first part. Thanks, everyone.
All right. So I think we can continue. Neel, do you want to start?
Yes. Yes, is it visible?
Yeah, perfect.
Yes. So my topic is on the hardness of safe bribery in voting, and it is joint work with Palash Day and Faraz Malik, who's here. So voting theory is designed to address problems which have multiple decision makers or voters who have conflicting preferences over the relevant alternatives or candidates. An election on the basis of a voting rule decides the winner. Bribery is a common problem in which an external agent tries to affect the results of an election dishonestly. The briber usually pays the voters to vote according to her choice while staying within her total budget. So there are a few applications of bribery, like in elections where candidates have campaigns to promote themselves, and also in the illegal sense, which is kind of a literal example, where candidates can use financial incentives to sway voters' votes. So as usual, A is the set of alternatives or candidates, and V is the set of voters. And a vote here is a complete linear ordering over the alternatives. So the voting rules which we consider are anonymous and efficient. So in an anonymous voting rule, the result is independent of the permutation of the voters. And an efficient voting rule is one in which the winner can be computed in polynomial time. Here we look at some scoring rules, where a scoring rule is a subset of voting rules where the voters assign a non-increasing integer sequence of scores to the alternatives. For tie breaking, we use an initial ordering over the candidates. And here in our model, the briber also has a preference ordering over the candidates, with C being her most preferred candidate. We call bad candidates those candidates who are below the original winner in the briber's ordering, and the rest are good candidates. So the voting rules which we study are some common ones, where in plurality, we only look at the first position of each voter and the highest one wins. In K approval, we look at the number of times a candidate appears in the first K positions. In veto, the candidate which occurs least times in the last position wins. In K veto, the candidate which appears in the least times in the last K position wins. And in bolder, as shown in the table, it's the decreasing sequence of integers. So dollar bribery, as introduced by Leizerovich et al., has briber who has a budget, and each voter has an associated price, and the briber pays the voters to vote according to the briber's suggestion, and the briber tries to make her preferred alternative win, which is pink here. So shift bribery by Elkind et al. Is similar, but here the briber can only suggest to move her preferred alternative up in the voter's ordering. So the pink one is shifted up in the briber's suggested ordering. So here we introduce safe bribery, where a bribery is said to be safe if the winner of an election cannot worsen with respect to the briber's preference order, no matter which subset of bribed voters refuse to follow the briber's suggested preference order. So here's a small example of plurality where there are 11 voters and 4 candidates, and we first 5 vote for A, 6 to 9 vote for B, and 10th and 11th vote for D. And this is the briber's preference order, and this is the suggested preference order to V1 to V5. So original winner is A, and only if V1, V2, V3 vote CA, BD, the election will not be safe. So we introduce problems dollar bribery is safe and safe dollar bribery. In dollar bribery safe, we already have a bribery, and like our goal is to find that if a subset of voters don't vote according to the briber's ordering, can a bad candidate win? And in safe dollar bribery, we are given a budget and prizes, and we actually need to find the subset of voters to bribe and the orderings to suggest. The same problems are defined for shift bribery analogously, but here in terms of safety, it is possible that the voters do not shift the briber's preferred candidate up completely. So partial shift also has to be taken into account.
You have 20 seconds left.
Yes, and these are some of the results which we obtained for the scoring rules. The blue ones use flow network. The brown ones are reductions from a variant of set cover. The yellow one is greedy. And the purple ones are reductions from dollar bribery and shift bribery. And the green ones are in brute force. Yes, so thank you.
Thank you.
These are some, yeah, and the future works.
Okay, thanks a lot. If anyone has questions, feel free to ask them. I was wondering, in the dollar bribery versions, can the briber suggest any ordering to voters, or must they suggest their preferred ordering?
Any ordering.
Will it ever be optimal to suggest something different from the preferred ordering?
It could, like, I'm not sure, like maybe it could help. Maybe it could help for safety. Like maybe I'm not exactly sure. But, in scoring rules, I don't think it would help.
Right. You could imagine other voting rules where it's more complicated, I suppose. Yeah. Okay. Thank you. And I think then other questions via the chat, we can slowly move on to Fatima's next.
Thank you.
Thank you.
Should I start?
Yes, please. Go ahead.
Okay.
Thanks.
So hi everyone, my name is Fatima, and today we'll be talking about accomplice manipulation of the deferred acceptance algorithm. This is based on joint work with my advisor, Hadi Hosseini and Rohit Peish. So our work deals with the stable marriage problem. And to give just a brief overview, the idea here is that we have a two-sided market such that agents on each side have preferences over agents on the opposite side. So here we're using the example of a market with workers and firms. So the deferred acceptance algorithm, or DA algorithm for short, is widely used in these types of two-sided markets because it's guaranteed to find a stable matching in polynomial time. In other words, it finds a matching such that there exists no worker-firm pair who prefer each other over their assigned matches. Unfortunately, however, the DA algorithm has been shown to not be strategy-proof for exactly one side of the market. That depends on which version of the algorithm is used. Here we'll assume the worker optimal mechanism, which means that the firms have incentives to lie. And so I won't go into too much detail here, but in this instance, Google benefits from submitting a false preference list. And we refer to this type of strategic behavior where firms misreport by promoting their own preferences as self-manipulation. But the question then is, can we do better? And in our work, we study a new model of strategic behavior called accomplice manipulation that was introduced by Benlin and Hosseini. So let's consider the same example again. Here we'll assume, again, that Google is a strategic firm, but instead of Google submitting its own preference list, misreported preference list, it this time convinces worker D to misreport on its behalf. And so the resulting outcome matches Google with its top choice A. And notice that worker D also remains matched with Apple, just as it was under the original preference profile. And compared to the self-manipulated instance from before, Google is strictly better off after accomplice manipulation because Google prefers worker A over worker B. Now to more formally state our model, under accomplice manipulation, a strategic firm teams up with a worker, who we refer to as an accomplice, to manipulate the DA outcome on its behalf. So the accomplice misreports and the strategic firm remains truthful. And there are two cases we consider, one being the no regret case under which the accomplice retains the original DA outcome. And then the other is the with regret case under which the strategic firm convinces the accomplice to match with someone they less prefer, perhaps through some side payments. Here I'll only focus on the no regret case, but in our paper we do consider the more complex with regret setting. And so experimentally using uniform random preferences for different numbers of workers and firms, we compare the fractions of instances where a fixed firm is able to improve through accomplice manipulation and through self-manipulation. And so clearly the fractions for accomplice are nearly double the fractions for self. And that was just comparing the strategies against truth-telling, but if we compare the strategies against each other, then the results are actually even more compelling. So the plot here suggests that accomplice manipulation is not only more frequent, but also almost always a more preferable choice. And so similar models to ours have been studied before, especially when it comes to the problem of matching students in colleges in countries where variants of the DA algorithm are used. So when the college optimal mechanism is used, for instance, Belinsky and Sonmez showed that students may have an incentive to perform worse on tests in order to make themselves appear less preferable to certain colleges. And similarly, if the student optimal mechanism is used, Hatfield et al. Showed that schools may deliberately make themselves look less attractive to undesirable students. And in both of these cases, the proposed to side is like indirectly altering the preferences of agents on the proposing side, just as with our model. And so there are a few natural questions that we would like to answer. One is, how do we compute an optimal accomplice manipulation strategy? And then the other is, how does the strategy affect stability? So to start, let's answer the first one. So looking back at our example again, we see that the misreported list of worker D, who remember was the accomplice, can be created just by moving Microsoft above their DA match Apple. And we refer to this type of manipulation as inconspicuous. More formally, an inconspicuous manipulation is one that can be achieved by promoting exactly one firm. And so the main result of our paper says that if there is an optimal no-regret accomplice manipulation, then there must also be an optimal inconspicuous no-regret accomplice manipulation. And so this then immediately implies a simple polynomial time algorithm for computing optimal no-regret strategies, because all you really have to do is try promoting each firm in the accomplices list and then return the strategy that's best.
Please wrap up, please.
Okay, so just to wrap up, we show that the set of all stable matchings with respect to the inconspicuous no-regret accomplice manipulated profile is contained within the set of stable matchings with respect to the true profile. And I'll end there.
Thanks very much. Again, open to questions. You can either like raise your hand or write in chat. You mentioned towards the end about optimal manipulations. Does optimal mean anything else than it works?
So optimal means that out of all the set of all no regret accomplice strategies, it's the best one. So there may be multiples. So can the no regret accomplice manipulation be reinterpreted as a violation of non-bossiness? Yeah. So. Right, because the accomplice who's misreporting is affecting the matches of all the other agents without like ruining his own match.
I think no regret was defined as you keep your previous match. You could also define it, keep it or get a better one for you, like for the accomplice.
So it's not possible to get a better match for the accomplice due to the strategy proofness results.
Oh, of course, yeah.
But yeah.
Okay, thanks very much, Fatima. Péter is next.
Hello, can you hear me?
Can hear you, yeah.
Can you see my slides?
Yeah, looks great.
Okay, so I have no paper to present. This is just really an open problem motivated very much from the application, which is the election in Hungary, where we have the same government for the last 11 years. So next year we will have the next election. Orban with Fidesz is the current governmental party. They have around 1/3 of the voters. Actually, the quarter of the voters, they have no party, and the rest have, small parties that they support. And these parties in the opposition are very different, like conservative, populist, and social democrats, liberal, green parties. But this year they decided to unify and to actually try to win the next election. And the reason why they needed to unify is can be shown with a simple example from 2018 when we had the last election. So the opposition could not really coordinate. So they made some agreements, some collusion happened between the parties, but still there were many districts. So actually the election is for 200 seats in the parliament, and 106 are elected directly with a simple plurality voting. And therefore what happened in many districts is that there were several candidates from the opposition, and the governmental candidate won. Like in this district when I voted, they had like 41% the government, and then the next candidate only 1% less. And you can see that there were actually some parties in the opposition still with 6%. And the reason was that there was no really coordination, and some of these candidates were quite bad actually. Okay, now the year after, the opposition decided to do pre-election polls before the election for the local authorities. And that's how actually they could win the big cities, including Budapest. And this year, they also agreed that they will have one single candidate jointly selected by the 6 main parties in the opposition. But how to do that? How to do this pre-election and the selection of candidates for each voting district? So what they decided is the simplex method, just to have one round plurality voting in each district separately and simultaneously. And you can see that there will be many problems with the coordination, and also, so I will talk about a bit later. So there were some alternatives suggested, like 2 rounds of voting or approval voting in each district, or this London voting where there was just 1 round, but 2 votes, first and second votes. So actually these alternatives could probably give a better result. But I also had an idea, a proposal that I would like to present and ask your opinion. What do you think? How does this fit in the literature? Because I'm not familiar with the literature. So this proposal is a balanced vote exchange by central coordination, which is essentially a proportional committee selection. So what's the problem with the current system? So the parties should collude, obviously, and they collude strategically, and the solutions can be very unfair, unbalanced. So that's what happened in 2018. That's why there was no agreement, and actually resulted in a 2/3 majority again for Fidesz, the current government. So this year also they fight with each other, and even if they can agree on one single candidate, then this candidate is not selected by the pre-election. It's just behind the curtains, they are agreed. So what would be the proposal? The alternative proposal is to have a balanced exchange where each voter could give his or her favorite candidates, and then the acceptable ones as well. And we assume that the voter would cross-vote to the acceptable candidate. So there can be many objectives, like maximizing the total number of first votes or the total number of votes, which would lead to a single member plurality voting or approval voting if balancedness is not considered. But if we have balancedness, then actually the solution is kind of fair, where the reciprocity between the parties and voters would be respected. And essentially this would mean a proportional voting with respect to the first vote. Okay, so this is the last slide. So what are the questions? Would the overall result be better than the current one? Could we get better candidates, less fight and less deals behind the curtains? And better incentive actually also for the voters to cross-vote. What is the trade-off between balancedness, optimality, strategic issues for the parties and for the voters? So are there any applications of similar kind? I don't know really. There are some websites when you can organize swaps, like in the UK, but I don't think there is any organized swap between parties. But there are many related applications with exchanges without payments, like time banks or financial clearing, where actually there are one-to-one exchanges. So I'm really just curious whether you know anything about such an application, and I'm very happy to receive any advice on this topic.
Thanks very much. We have a few questions. So Jerome just asked whether we can see this as a form of primaries, like in the US.
Oh, I don't know. I don't know. So I should have a look. What are those?
And Hardy asked whether there's any issue with similar ranked choice voting that was used last week in New York City to solve this issue.
So please write me these applications by email, and I will try to look it up and answer, because right away I'm not sure what to answer. But yeah, probably there are many similar cases. So essentially they just have to coordinate. And that's why I said that it's a kind of committee selection, because they have to agree on, 106 candidates, but still, these voting districts are different. So in some cases, the right-wing populist parties are the most likely to win, and the other cases, like in big cities, it's more like liberal or social democrats who have chances. So it's really not just a simple, committee selection. Okay, so I'm happy to receive all your comments by email. Thanks.
Thanks very much, Peter. Next and last talk is by Sricharan.
Yeah, can you see my screen?
Yeah, we can't see your video.
Yeah, I'm running on mobile data, so I'm not
Okay,
sure how good it's going to be, but let me turn it on. Tell me if it lags.
Yeah, the audio is worse, so probably better to turn off video.
So, is it better now?
Yes.
Great. So yeah, I'm Sricharan from Chennai Mathematical Institute, and I'll be presenting work with Umar and Rohit on approximate NV freeness for indivisible chores. So the setup we'll look at is the following. You have some agents, you have some items, and all the agents have some valuation for the items. You want to find out a way to allocate all the items to the agents in a fair manner. There are two kinds of items you can look at. The ones which are desirable, which we call goods. For example, when you want to allocate courses to students. And when the items are undesirable, which we call chores. For example, there are household tasks which you need to divide among people. First, let's look at the goods setting. Suppose you have some goods you want to allocate to people. One notion of fairness that's been well studied is the notion of NV freeness, which says each agent would rather have their own bundle than someone else's. So the valuation for the bundle you give an agent should be at least as good as their valuation for other people's bundles, right? And it turns out if you're not allowed to divide the items into smaller pieces, then NV-free allocations do not always exist. For example, if you just have one item which you want to allocate to two people, you can't find an NV-free allocation. So you need relaxed notions of NV freeness. One of which has been well studied, is the notion of envy freeness up to one good. So this allows for envy. So I might envy the bundle you have, but this envy will vanish on removing one good from your bundle. Right? So as you can see in the previous example, this has an EF1 allocation. Just give the toffee to anybody. How do you get an EF1 allocation? Well, there's an algorithm called the envy cycle elimination algorithm, which iteratively assigns items one by one. And the invariant which this satisfies is that at each step of the algorithm, the allocation remains EF1. And the algorithm is simple. Let's just go through it once. You have an envy graph where you have the vertices of the graph as the agents, and you draw a directed edge from an agent to the other if A envies B. So how do you start allocating items? First, all the items remain unallocated. You take an item, give it to some agent who's not envied by anybody else. So it should be a source vertex in this graph. And so once you give an item to an agent, the envy might change. You update that in the graph. And you keep giving items to source agents in the graph. Sometimes you might come across cycles in the graph. But when you have a cycle, there's one nice thing you can do, which is reallocate the bundles backwards along the cycle, because everybody likes the bundle they are pointing to. So you resolve cycles like this, which also preserves EF1. And so the algorithm is simple. Whenever you see cycles, resolve the cycles. And modulo that, keep allocating new goods to sources in the envy graph. Both of this preserves EF1. This is nice. What if you want to divide chores among people rather than goods? Of course, envy-free allocations would not again exist, because if you have one chore, you don't know who to give it to. You need relaxations. A similar relaxation would be envy-freeness up to one chore. What would the definition be? Well, I might envy you, but that envy should vanish on removing a chore from my own bundle. And this gives rise to some asymmetry between EF1 for goods and chores. In goods, to satisfy EF1, you remove a good from the envied agents bundle, whereas to satisfy EF1 for chores, you remove a chore from the envious agents bundle. And this causes problems when you try to adapt the algorithm naively here. What would you try first? You try the same algorithm as before, but you'd allocate new items to sinks in the graph instead of sources, right? Well, it turns out if we try that, allocating new items is not a problem, but resolving cycles is a problem. Once you resolve cycles, it might happen that finally you might get an allocation which is not EF1. In particular, in this example, you have envy, which does not go away on removing one chore. So how do we fix this? Well, it turns out there is a nice fix where you don't resolve arbitrary cycles. You don't resolve any cycles that come up. You only resolve specific cycles, which we call the top trading envy cycles. What are the top trading envy cycles? In a normal envy graph, you have edges to all the bundles you envy. Whereas in the top trading graph, you only have edges to your most favorite bundle. So it will be a subgraph of the envy graph. And it turns out if you just resolve only the cycles in this top trading graph, then that gives you an EF1 allocation. And this is still polynomial time, which is nice. And you can even extend this to classes where you have both goods and chores. And my idea of what's a good might be different from your idea of what's a good. And we still get EF1 allocations, which is nice. So yeah, and I also have some open questions left up. No, I think that's all I had to say.
Thanks very much. Is this the first algorithm that gets EF1 for chores?
So if you have additive valuations, round robin works.
Oh, I see. Mm-hmm.
Whereas if you want it for monotone valuations, so an earlier claim said just the naive algorithm will work, but it turns out it does not because of removing the chore from your own bundle. So you'd need the top trading cycle to fix that.
And by resolving top trading cycles, do you actually resolve all the cycles just in a different order? Or are there cycles that remain like in the full envy graph through most of the execution of the algorithm?
Yes, so your final allocation might still have envy cycles left.
Okay.
We have an algorithm which removes those envy cycles and gives an EF1 for additive chores.
Mm-hmm.
Oh wait, which is based on the round robin algorithm, but not for monotone.
Okay.
So in particular, having those cycles causes a problem when you want to add goods after adding the chores. So you need to add goods and then add chores. If you try to add goods after adding the chores, that doesn't work.
Oh, interesting.
Yeah.
All right, thank you very much. These are all the talks. I propose that we go back into breakout rooms so you can ask any questions that have come up during those talks. But let me quickly announce the next COMSOC seminar also, which is in 2 weeks, when we will hear from Vincent Merlin and from Nick Matai. So that's in 2 weeks on the 16th of July. Okay, thanks very much for joining, and I'll see you in the breakout rooms.